Welcome back. We have another problem here on the concept of this chapter, modeling of translational mechanical systems. But let me quickly make a correction to something I had said previously, which was the fact that we called C, that's C for the dashboard or the damper, we called it damping constants. Okay, to avoid confusion, please always call that coefficient of damping. Okay, so that is that about that. Please just take note of that, okay? So that it doesn't get us into unnecessary confusion, okay? So let's move on now. So we have this system. We want to get the mathematical model for these systems, okay? Right here again. So what is so special about this? In this case, we have this to be restricted at two ends. Okay, this is also we have two masses here. Here we have three masses, so we could have things that get complicated like this. But then the idea, the approach, the concept is still the same as what we have applied before now. Okay, so let's get into it and see how this works. So for the first one, A, for the A part, let us, as usual, produce a free body diagram, not so free, but a free body diagram anyways, for the body. So we know that some force is applied here to actually move the body. We know the actual values of these constants that we need. So we know the actual values of all of them. So we're good. Here F is applied and it's directed to the right. So we're going to give this a rightward displacement. So let's say that that mass has some rightward displacement. So with that some rightward displacement, we can indicate that here. Okay, it's a horizontal displacement. We call that x. Okay, so it has some displacement x to the right. We know there is the external force F that facilitates that. Let's indicate that here. So we have the external force F. Okay, we know it is equal to 90 cos omega t as provided. Okay, whatever that happens to be, of course, that will be in Newton anyways, consistent with what we have in this system. And then for this, there will be a force that opposes, will be always opposing the motion of the body. Okay, so we're going to have this directed, to the left since the displacement is to the right. So this is force due to the dashboard. Okay, and then we have the forces due to the springs. Okay, so we have those directed to the left as well. So this is going to be here F sub S, and then this also F sub S, both directed to the left. And by that, we know that we have some mass right here. So we can write out, we have taken care of everything that we need to take care of right there. There will be some normal reaction up and down, but they are not relevant to our analysis. Okay, so we have taken care of everything that is relevant to our analysis here. So with this, what do we have? We know that F sub S, let's quickly write them out, will be equal to Kx. Okay, the same for both of them. The spring constant is the same for both of them. So basically, we just leave it like that. And then we know F sub D will be equal to Cx dot. Okay, so that's all. And with that, we are good to go. We now take summation of forces in the direction of motion. We know that is F. Only F is along the direction of motion, so that is positive. Then the others are opposite the direction of motion. So this will be minus F sub D minus F sub S minus F sub S. That is F sub D here, F sub S here, then the second one here. So all of this must be equal to the mass of the body multiplying its acceleration, which is x dot dot. Okay, so that is that about that. Let us have an additional page. Then we know that by the time we put all of this together, we'll have mx dot dot, then we know f sub d just once and it is cx dot, and then so it's negative here. When we move to the other side it becomes positive, so this will be plus x cx dot. Okay, then we have f sub s, both of them negative. When we move to the other side that becomes plus 2 f sub s is kx, so put this as kx, and f remains where it is as this. Okay, so that will be the mathematical model for this system. Okay, life can be just as easy as that. And we know the actual values, so we can just insert those here. We know this to be 400, we know C to be 125. All of them are in They are SI units, so we don't have to bother about those. So this will give us the mass also is provided. What is that mass up there is 20 kilograms. So we're going to put that in as well. So we have this to be 20 multiplying x dot dot, then plus c. We have C up there. Let's us check that again. To be 125. Okay, C is 125. So let's say we have 20 here plus 125 multiplying x dot plus 2 into k, which is 400 as provided there, multiplying x is equal to f. F is given by 90 cos omega t, okay, as provided up there. So this is 90 cos omega t. And with that, we are good to go. We can now tidy up everything we have here and get our final expression for the mathematical model for this system. So we have this to be equal to, so we can divide through by 20 or divide through by 10 or whatever, but let's leave it this way anyway. So this is going to be 20 x dot dot plus 125 x dot, then plus 800, so 2 multiplying 400, that is 800 multiplying x equals 90 cos omega t. Okay, and that is all for that problem. 90 cos, what am I writing omega t? 60 actually, 60. So it's not omega, it's 6 is there. So this is 6, please. Let's correct that and just move on. So this is cos 60, this is cos, and that is all for this problem. We now have the mathematical model for the system. Nothing else is required of us here. Of course, you can give it a try personally and try to solve the differential equation. Okay, if you don't know how to solve differential equations, you can have a look at the course on ordinary differential equation and just to refresh your memory. Okay, so let's move on. We just need differential equations, the mathematical model, and we have them now. Okay, so we just move on to the next one. So we have for the problem B. So for the B part, we draw a free body diagram, but this time around we know there are two masses present, so we have to consider both masses. So we draw for M1, we draw for M2, and that means unavoidably we will have two equations in our mathematical model. So one will be for M1 and the other will be for M2. So we can do that right away. We draw a free body diagram for M1. We'll have something like this. So let's indicate that that is for M1. And then for the others, what are the forces? So x1 has been indicated for us already. So we're taking the direction of its displacement to be positive to the right. And so let's indicate that that is x1. Okay, of course, as function of time. Okay, that's just telling us x1. Okay, we know it changes with time. And we indicate all of the forces acting on M1. So there is a force here due to this damper. So the damping constant, or sorry, the coefficient of damping is B here. So the same thing we typically denote it as C. So that's what is being denoted as B here. It makes absolutely no difference. It just means we'll be using B as a notation instead of C as a notation. So we're good. So this is going to be B, and then let's insert the forces first. So we know that if this displaces, if this is displaced to the right, all of this will oppose the motion. So they will all be directed to the left, including those due to K2 and K3, because this body is connected to K2, K3. So we'll indicate all of that now and direct them all to the left. So we put that here. That is force due to K2 or spring 2 if you like, or that fs2. We cannot just use fs arbitrarily now because these are two different springs with two different spring constants k. So we're going to put this here. This will be f sub s3, okay, just as we have it right there in the diagram. So this is K2, K3, and then there is K1 connected to the body as well. Then this damper or dashboard connected to this. So we're going to put all of the forces due to that, also direct them away or opposite to the displacement. So this will be directed to the left, and that is F due to spring 1, and then this is also directed to the left. That is F due to the dashboard, so we can call that D. Okay. If there were two or more of them there, of course, we'll also say this will be FD1 and then the other will be FD2. Okay, so those are those components that are directly linked or connected to this mass M1. So those are the things we're concerned with as far as M1 is concerned. As far as we're concerned with M1, these are the things we're concerned with. Okay. Bad grammar. Forget about that. Okay. So let's move on. This means we can now write our equation of motion for this body. So let's get that done for the mass M1 first. Okay. We'll come back to M2. So for this, we will have the forces here. This is the direction of its displacement. None of the forces is along the direction of its displacement in that it doesn't have any driving force directly attached to it. Okay, so we have that to be 0, nothing along the direction of displacement, so that is 0. Then minus all of these opposite the direction of displacement, so that is minus fs1 minus fg minus fs2 minus fs3, and all of this will be equal to m1 multiplying its displacement, which is x1 dot dot. Okay, so that is mass multiplying acceleration for the body. So with this, we're good. So the next thing we have to do and carefully choose is how to get the expressions for fs1, fd, fs2, fs3, and so on. Okay, so but we know that by the time we tidy this up, for instance, we know this is going to give us, we'll move all of them together with this, we're going to have this to be m1 x1 dot dot, then plus fd. We know fd is going to carry some x1 dot or something like that, so let's write that first. So this is f sub d. We're not writing in the expressions for now, and I don't want to write them out here so that it doesn't cause confusion when we want to consider the second mass. So this is f sub d, then we have this to be f sub s1, then plus f sub s2, then plus f sub s3. So all of this will now be equal to 0 since there is no force here. Okay, so with this we good. So we now ask ourselves, what do we have, or what will f sub d be? Let's start with that. F sub d, we know the coefficient of damping here is b, so this should be bx dot, okay, or b whatever position dot. Yep. So in this case, we ask ourselves, yes, we're dealing with the mass m1. If the mass m1 has this displacement x1, then how does that affect the length across this damper? We know that will also increase or change the length across this damper by x1. So we will still take this as b or c, if you know, as we used to, x1 dot, but in this case b is what we're using as the coefficient of damping, so we have this to be b x1 dot, because when this is displaced by x1 to the right, the length across this damper also changes by x1 precisely. So by that we will put that here, so we can say that what we have here would give us m1 x1 dot dot, then plus this will be k, sorry, I'm not using k now, please, b multiplying x1 dots, okay, because of that. So we've taken care of fd now. So we'll move to the next one, take them one after the other. For fs1, so let's think about what would happen to fs1 as well. If this is displaced, the mass m1 is displaced by x1, by how much will the length of this change? It will also change by x1. I mean, this end is fixed here, so it is not that anything is happening at this end that might decrease that length or affect that length. The length here will change by x1 directly. So for this case, we can easily see that the force due to this spring will be simply k1 x1. Okay, so we're going to write that as it is, k1 x1. So we have this to be k1 x1 plus, so let's move to fs2 now. For fs2, so this is the spring 2. If this body m1 is displaced by x1, by how much will the length of this change? That's what we're interested in. So by how much will the length of this change? If this is displaced by x1, we know that this other end is not fixed because this is some mass here that will also have some displacement, okay? Unlike what happens at this end where this is fixed. So this will also have some displacement, x2, okay, as noted here. So if this has some displacement x2 to the right, now this one goes x1 to the right, this also goes x2 to the right, then it means the displacement of this, which is the body we are focused on, will overall be x1 minus x2. Because imagine that this goes to the right by 3 meters and this goes by 1 meter. That means altogether the difference in length that will have happened to this would be 3 minus 1, okay, as far as we're concerned. So that will be x1 minus x2. So the force due to this spring will be K2 multiplying x1 minus x2. So let us insert that now. So this will be plus K2 multiplying x1 minus x2. Then we have the last one, which is force due to the spring 3 on this mass. So let's get back here. So this is the spring 3, okay, your guess is as good as mine. That is the same thing because if this goes to the right by x1, this goes to the left by x1, then the displacement of this body, which how that influences the change in length here, that will be given by x1 minus x2 as well. So that will be K3 into x1 minus x2. So we have that to be K3 into x1 minus x2. And all of this will be equal to 0. So that's all. We've taken care of everything. And that is everything we need to have here. So we can leave it this way. You may also say, okay, this is x1 plus, this is plus x1, this is plus x1, and then tidy it up and write it another way. Now that is not necessary, but if you do it, it's also fine. This will give us m1 x1 dot dot plus b x1 dot then plus, so you can see x1 k1 x1 here, k2 x1, k3 x1. So we can say we have k1 plus k2 plus k3 then multiplying x1. Okay, that's what we have here. K1 x1, k2 x1, k3 x1. Then the others are negative. So this is minus k2 x2 minus k3 x2. Okay, so we can say then that we have negative then k2 plus k3 multiplying x2, and all of this is equal to 0. So you can write it in this form as well, so that we always have this some expression multiplying x1 and then some expression multiplying x2. So that's all we have to do for this part. Okay, that is for mass m1. So we can keep track of this result and call that equation A, for instance. So what is the next thing to do? We will focus on the mass M2 now and get its own equation as well. So we draw a free body diagram, okay, for the mass M2. So let us quickly do that for mass M2. So what we just did is for mass M1. Now considering mass M2. So we do the same thing for mass M2. We know that its own position is captured also already indicated for us. That is x2 as a function of time, whatever you put there. So that is x2 for its displacement. And then what are the forces to consider here? There is the driving force, okay, which is F of t. So we're going to put that in. And then there will be force due to the spring 2, force due to the spring 3. Now all of them also directed, opposite this, okay. So this is directed along the displacements and the others will be opposite to that. So we quickly put that here. We'll have this to be F, which depends on T, and then there will be the opposing forces, that is force due to spring 2, and this is force due to spring 3. So that is that about that. Yes, you might be wondering, how about the weight of the body? How about the friction and all of that? Those are not relevant. Friction is typically ignored, and weight is not relevant because it's in the vertical. The normal reaction is also not relevant here. So even if we were considering a vertical situation, the weight will still not be relevant, as we saw in the last lesson. Okay, so with this, we are good to go. We can now write the equation of motion for this. So along its direction of motion, we have F, so we can put that as plus F. Then opposite, we have negative Fs2. Opposite also we have negative Fs3. And by that, we say this will be equal to, I mean, that is all we have for the forces on M2. So this will be equal to M2 multiplying its acceleration, which is x2 dot dot. And by the time we tidy this all up, we're going to have this to be mx2 dot dot. Then moving this to the other side, that will be plus fs2, then plus fs3. So all of this will then be equal to f, okay, the first f that we have there, okay, that depends on time. And that's all. So what do we need to do now? Get an expression for fs2, get an expression for fs3. So you have to be careful here as well. So this is mx2 dot dot. This is plus. So what is fs2? So you might be tempted to say that it is the same thing as what we have here. Okay, we used fs2 here as k2 into x1 minus x2. If you do that here, you will be walking in error. So that will be wrong. And I told you earlier that we avoided writing out formulas for them like we did here, okay, because we didn't want to run into that error. Because if we had written out that formula here, you would be more tempted to just substitute it here and move on, okay. More so because the directions are even the same. So we have fs2 to be directed to the left here, fs3 to be directed to the left, and here also this is directed to the left, this is directed to the left. So it is very, very tempting to just say that, oh, this is going to be the expression for fs2. We already have it up there. Let's insert it. No, 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 please, you don't do that here. Okay. So what do we do now? fs2, we have to go back and consider the body. We know that this equation here we're using is for this body. Now, one thing you should know is that in reality, what happens is that if so just think about this for a moment. If this body, if this spring was under compression, that is, it has been compressed. Okay, imagine that these two bodies are positioned such a way that the length of the spring is lower than the natural length. Then, if the spring is under compression, we know that it will push on this rightward mass, that is M2, and it will pull, okay, so to speak. Now it will push on this. I mean, it will want to extend itself. So the force it will exert on this will be this way, and the force it exert on M1 will be this way. They will be opposite. So this will be M1. That is, if this was under compression, if any of this, okay, was under compression, they will actually want to push those bodies away. Yep. So that means the forces will be directed opposites. And if now that is for it when it is under compression. So imagine that it's actually under tension. So if this spring was under tension, then what do you think the effect will be on these masses? If it was under tension, so if you consider the mass M2, it will be pushing this mass M2. Okay, it will be pulling it, okay, to itself because it wants to restore itself to its equilibrium position. So it will pull on this to the left. And on mass M1, how will it do? It will also pull on it because it will want to get restore itself to its initial position. So that is the idea. So we see that in reality, whatever force is being exerted by this spring, okay, to on this body will be opposite to that on this body. That is reality. But in the free body diagrams that we have drawn here, we can see that fs2, fs3 are both directed to the left here. They are also directed to the left here. In reality, that is not so. So we got this here to the left, and we are doing it here also to the left. We know in reality that is not the situation. So we should suspect reasonably that if we are giving them the same directions, they should have opposite values. So that is, we should be giving this the negative of what we gave it here, because in reality they should be opposites. Okay, so that is why we usually have to go back and consider the specific body we are analyzing so as to obtain that expression. We don't just use the expression that we have used for one on the other. No, we have to go back and consider the specific body that we are analyzing. Here, we're analyzing the body of mass M2, so we have to go back and consider the mass M2. So if we have the mass M2 displaced to the right. Yes, the first setup here should be K2X2, but we know this will also have some displacement. So if this has some displacement and this has some displacement, then the displacement caused by this, or the effective displacement or the effective extension of this spring due to this mass, will be X2 minus X1, because if x2 does not take place, then it will just be due to x1. So if x2 takes place, that is if x2 is not 0, then the effective displacement at the end of the day will be whatever x2 is minus x1. So this time around we'll be using x2 minus x1 and not x1 minus x2 like we used for the body of mass m1. Okay, so that is what makes the difference. So using x2 minus x1 here instead of x1 minus x2 that we used here already takes care of the fact that in reality this should be oppositely directed. But now we are giving them the same direction, then how to take care of what happens in reality is to actually arrive at a situation where they have opposite signs. Okay, and that is literally what we get when we take that into consideration. So this is going to be so the fs2 on this body will be k2 x2 minus x1. Okay, so imagine this goes this way and then this also follows. So the effective difference in length that it causes here will be x2 minus x1. So x2 minus x1 and x1 minus x2 will give us the same numerical value at the end of the day, but they will give us different signs. So that actually captures the fact that the directions will be opposite. Okay, so I think we've said enough already. So that will be k2 into x2 minus x1. So let's quickly write that out now. So for fs2, we're going to have this to be k2 into x2 minus x1, x2 minus x1. And then for fs3, similarly, we get k3 into x2 minus x1. Okay, it's just along the same length. Okay, so k3 into x2 minus x1. So let's insert that here. And is that all? Yes. Then we have this equal to f because the first f is applied on it. And then can we tidy this up even further, make it a little bit more presentable? We say this is m2, please, m2. Okay, to differentiate it from m1, it's essential to put that subscript. So this is m2. So m2 x2 dot dot. Then we have this to be, so we can see plus k2x2 plus k3x2. So we can say this is going to be plus k2 plus k3 multiplying x2. Then we have this to be negative k2x1. So this will be negative k2 plus k3 into x1, and that is equal to f. Okay, we can say f of t as given up there. All right, and that is our second equation. Okay, we can call that equations as our equation b. So equations a and b give the mathematical model for this system. That means we inevitably have two equations here because we have two masses. Okay, so the equations A and B give us the mathematical models. So we can put them together. We can now say that hence the mathematical model, okay, for this system is given by equations A and B. So that is that about that. Those two are the important equations here. So let us highlight them. Okay, we're done with this part of the problem. We now move to the C part before we end this lesson. So for the C part of this problem, so here we have um, this system. We can see we have masses M1, M2, M3. That's a lot. We have the applied force F. Good, but that is on mass M3. So it won't affect the other masses because it's not directly applied to the other masses. And then this is displacement input. So that means this end is not fixed. So there is some displacement here captured by y. So it is unlike this where the end is fixed. Here there is going to be displacement of this end. That is what this means. Okay. So we have to consider as before the masses one after the other and derive equations for them. So that means that the mathematical model for this system will comprise three equations. So let us get into that. For the mass M1, quickly draw its free body diagram. So K1 is not indicated here. Let us quickly put that. This is some spring, and the spring constant is K1. So let us draw the free body diagram for mass M1. So we know it is connected to the springs. So we say that for mass M1, mass by mass, consider this mass by mass. So for the first one, M1, let us just put that in here. We know it has some displacements x1, so indicate that as well. It's in this direction x1. So the spring force due to this will be opposite that displacement. That will be F, okay, due to the spring 2, and we'll have F due to the spring 1. So we'll put that here, F due to spring 1. So that is all for the mass M1. Okay, these are the two springs connected to it. This is K1, this is K2, this is K3. Okay, this is C. Okay, and then we know that we need to get expressions for both of them, but we'll come back to that. Let us firstly write out the equation of motion for this mass M1. So to follow that, there is no force in the direction of displacement. You can put that at 0, then minus all of these opposite the direction of its displacement. This is Fs1 minus Fs2, and this will be equal to M1 x1 dot dot. Okay. So with this, we can now put together all of this and say we have M1 x1, okay, dot dot, plus, we'll put this to the other side, Fs1, then plus Fs2, and this will be equal to 0. And with that, we are good to go. We now get expressions for Fs1 and Fs2, okay, for this mass M1 with respect to this mass M1. So this is M1 x1 dot dot plus, so let's get right into that for Fs1. So you need to be careful here because this end is not fixed as we noted earlier. Because it is not fixed, this will have or can have or may have or will have some displacement y, and we can see that is to the right as well. So if this has displacement y to the right, this has displacement y1, m1 has displacement y1. So if m1 is displaced by y1, how does that cause a change, or how does that influence the length of this spring k1? So if this is displaced to the right by y1, then we have to consider the displacement of this end as well. So that means the effect of the displacement of m1 on the change in length of this k1 is going to be y1 minus y, okay, because if this goes by y1, this is not necessarily extended by y1. That will depend on y. So if y goes to the right as well, positive, that means the displacement overall will be y1 minus y, okay, for this spring, okay, or the change in the length of the spring overall will be y1 minus y. So that means Fs1, as far as this body is concerned, will be K1 into y1 minus y, okay. Then we go to Fs2, the force on body M1 due to the change in length of the spring 2. So this is the second spring here. So if this is displaced as it is to the right, then we know that it doesn't necessarily connote a change in length of this, because that will also depend on y2 since it is connected to this end. So that will be y1 that it goes to the right with minus y2. Okay, so because if y2 happens, the displacement or whatever change in length here will not be directly equal to y1. That will depend on y2 as well. For instance, if y2 does not change, then this will be compressed directly by y1. Okay, and that will capture whatever change in length we have for this. But if this changes, we have to subtract whatever change is happening here. So that is y1 minus y2. So we have this to be plus k2 into y1 minus y2, and this is equal to 0. So we can leave it as it is. We can also why did I write y1 here, please? X1. So this is an error, please. This is the position of body 1. Okay, we've been using X for horizontal so far. Okay, that's why I have erroneously written that. But that the displacement, the position coordinates are already provided in the problem statement here. So we just have to stick with them. Okay, so that's why we continue just to use Y as provided, please. Okay, so this is an error. You can correct this at your end. I'm sorry about that. So this is Y1. This is y1. Okay, it isn't that we have two different things here, please. So this is still y1 dot dot, right? So this is y1 as well. Okay, so consistent with everything we have here. So we can now say that this is m1 y1 dot dot, then plus. So we can now say this is k1 y1, this is k2 y1. So we can put them together and say we have plus k1 plus k2 multiplying y1. Then, so this is minus k1y. Okay, we know y is an input as well. So it is an input, it's regarded as an input or provided as an input. So we might want to just move it to the right hand side because it's an input. So this k1y is negative here, we can move it to the right. Okay, then leave the others as they are. So this is going to be plus k2 y2. So that will be negative k2 y2, and then we can move this minus k1y to the right. That will become plus k1y. So this is a an equation that describes the motion of mass m1. Okay, so it will form part of our mathematical model for the system at the end of the day. So this is clear enough. We have moved this to this side because it is regarded as an input, just as we had so far. Always add this f, which is an input to the system. Okay, on the right hand side. Okay, so that's what we're putting this to the right hand side. That doesn't make it any less the same as having it on the left hand side. It will still have the same implication at the end of the day. It's just good to have all of our inputs on the right hand side. Okay. So that is that for the mass M1, quite straightforward to deal with. So we now consider now mass M2. We have three masses here. We have to consider all of them. So we say that for mass M2, what are we going to get? We do the same thing. Draw a free body diagram for the mass M2. This is mass M2. Indicate all of the forces on it. Okay. So there is no driving force on it. We're going to just indicate all of them as opposing the direction of its displacement y2, which is to the right. So all of those forces will be directed to the left. So we have for the mass M2, let us put that here. So this is mass M2. Then there will be the force here due to the damper or dashboards if you like. There will be another force here due to the spring. That will be spring 3. There will be some force here due to the spring 2. So we'll put that here, F due to the spring 2. And we know the displacement y as provided is positive to the right. Okay, so this is y2. So we can indicate that here. So this is y2. We good. That is all for the body. So for confirmation for the mass m2, we can see y2 is to the right. There is a dashboard here. So that's what we have put down there as fd. There is f. Okay, due to the spring 3, that's what we put as fs3. Then there's force due to the spring 2, fs2, all directed against its displacement. Okay, so by this also we can say the summation of forces along its direction 0, no force along that direction, then all of the other forces negative, fs2, negative, fs3, negative, fd. And all of these will be equated to the mass of the body, which is m2, multiplying its acceleration. Since its position is captured by y2, so this will be y2 dot dot. Okay, and with that we are good to go. So as our custom is, we put all of these equations together. We'll have this to be m2 y2 dot dot plus, so we can put the dashboards first because that will carry some dots. Okay, and then this is going to be plus f sub s2, then plus f s3. So we equate all of this to 0, right? So we can now get an expression or get expressions for the spring forces. So this is m2 y2 dot dot, then plus the dashboard force. We know that will be given by cy dot, but then how will y change here? how does y change here? So we can see that M2, which is our focus here, goes to the right. Yes, but when it goes to the right, that does not denote or connote a change in length of this or a displacement or a velocity of this given by y2 dot. It will also depend on y3. So at the end of the day, this will be y2 dot minus y3 dot because this damper is between body M2 and body M3. So at the end of the day, the velocity, or if you like, the rate at which the length of this changes will depend on the rate at which the length of this changes relative to this. Okay, so this will be y2 minus y1. Okay, so we have y2 dot minus y3, sorry, y3 dot, and that is c. So this will be c into y2 dot minus y3 dot. So put that there for fd. So this will be plus c into y2 dot minus y1 dot. Okay, and by that we are good to go. Then this will be plus fs2. Again, as we explained in the b part of the problems here, we are dealing with this mass now. So if it has displacement of y2, then the effect on this will be y2 minus y1, not y1 minus y2 any longer. So this will be y2 minus y1 multiplying k2 as explained earlier. So this is going to be plus k2 into y2 minus y1. And similarly, for the last one, that will be k3 into y2 minus y3 because it's connected to the third body. Okay, so k2 into y2 minus y3. That is evident in that if this is displaced by y2 to the right, this is also displaced by y3 to the right, then the overall displacement or change in length of this will be y2 minus y3. So that is that for the second mass, and we can tidy that up even further by saying that this would give us m2 y2 dot dot, then plus c into y2 dot y1 dot. Let's leave that as it is. We can say this is c into y2 dot. We can just multiply that out. So this is going to be c into y2 dot, then minus c into y1 dot. Then this will be k2 y2, then another k3 y2. So we can put them together and say this is k2 plus k3 multiplying y2, okay, y2, not y2 dot. And then we have for the negatives minus k2 y1 minus k3 y2. So that will be negative k2 plus k3 multiplying y3. Okay, so that is that about that. All of this will be equal to 0. So that is the equation we obtained from the mass m2. So we can call that equation b here. And that's all for mass M2. We're not done. We still have mass M3. So we're going to get the equation for mass M3. Considering mass M3, we will indicate also all of the forces on it. Of course, the force F is an applied force along its displacement. The others, due to this dashboard and also due to this spring 3, will be directed opposite its displacement. So that is going to give us this. So for mass M3, we'll have the following. We have the mass M3. So we have the force F directed to the right. Then we have its displacement y3 also directed to the right. So the forces here are directed to the left. So we have the force due to the dashboard and also the force due to the spring 3. So we have the force due to the spring 3, then the force due to the dashboard. So we can put that here, FD. So with that, we are good to go. Those are all of the forces acting on the mass M3. So you might say the weight. We've explained that already, that is not relevant here. So this is the equation, this is the free body diagram. So we can now write the equation along the direction of motion. We have F right now. So this is plus F, and we have these others to be negative. Minus F sub D minus F sub S3, okay, from the spring 3. So all of this must be equal to the mass m3 multiplying the acceleration y3 dot dot. And by that, we can make a rearrangement and have m3 y3 dot dot, then plus fd, the force due to the dashpot, then plus fs3, and then this is equal to f at the end of the day. So with this, we are good to go. We just need expressions for fd and fs3. So let us write out that result here. This will be m3 y3 dot dot, then plus fd, so the force due to the dashpot. Again, we know that in this case we're considering the mass m3, so that will be y3 minus y2. Okay, no longer y2 minus y3, so this will be y3 minus y2, so that is a c into y3 dot minus y2 dot. Okay, so we're going to put that here now, so this is going to be plus c into y3 dot minus y2 dot, and we close that bracket, and then this will be plus fs3, so expectedly also that will be k3 into y3 minus y2, because this is between y3 and y2, so that is k3 into y3 minus y2, no longer y2 minus y3, so this is k3 into y3 minus y2, and that is also equate this to f. And from here, we can tidy this up again and say we have m3 y3 dot dot, then plus c y3 dot, then minus c y2 dot, then plus, so in this case, we don't have any other expression to put together. So this is just k3 y3 minus k3 y2, and all of this will be equal to f. And that is that about that for this equation, so we can call this equation c. So with this, we have all of the equations that give us the mathematical model of this system. Okay, so we can now say that the equations a, b, and c give the mathematical model for this system. So let us emphasize the equations a, b, and c. Equation b, so yep, let's put that here, so this can come in here. Then equation c, we just obtained that. Right, so that is our equation. So observe the fact that we use y3 minus y2 here again because we're dealing with body 3. Y3 should come first, y3 minus y2 here, and this should be y2 minus y3. Okay, there's an issue here. Let us correct this, please. This is not meant to be for the f due to the dashboard. This is meant to be y3 y2 dot minus y3 dot. I mean the dashboard is between y2 and y3, not between y2 and y1, please. That is an error. Please let us correct that here for mass m2. This is y2 dot minus y3 dot. Yep, so that is okay. Yep, we're good. So this is meant to be y3 dots. Yep, we're good. So that is important. Please correct that at your end, okay? So let us correct this. There is an issue here, please. Oh my, we've messed this up. Please let us correct this. Y this is this expression here, this is meant to be c minus cy2 dot, yep, minus cy3 dot, yep, then k2y2, yes, that is k2 plus k3y2, but this is not k2 plus k3, please. This is k2 minus k2y1, then minus k3y3, so they ought to be separately written, please. Okay, minus k2, so K2 is going with Y1. So this is K2 Y1. Then minus K3 Y3. Okay, K3 is going with Y3. Okay. And if you find that confusing, please, you might just leave it this way. It's fine if you left it this way. Okay. So it just looks better this way so that we can easily relate the positions of the different bodies, how that relates to the dynamics of this mass M2. Okay, so yes, that is corrected. K3, K2 plus K3 multiplying Y2, K2, Y2, K3, Y2. Then minus K2, Y1, minus K3, Y3. Okay, I hope we didn't make any such mistake here. This is minus k2 y2. Yes, because that is the only thing present there. So minus k1y. Yep, good. We've moved this to the other side. Right. So I guess that is all for this lesson. And let us check this so that we didn't make anything like that. This is c k3 y3 minus k3 y2. Yeah, we're good. So I'll see you in the next lesson as we discuss some more interesting stuff about modeling of, say, mathematical modeling of dynamic systems. Thank you for watching.